Okay, hello everybody, we're back again. Next talk is starting now, and I have the honor to present Oscar Rodriguez Salona from Madrid. So we're also very international once again. And Oscar is a bachelor in computer science from Universidad Politécnica de Madrid, and he is specialized on artificial intelligence, and he is currently enrolled in a master program of bioinformatics by Universidad Autónoma de Madrid. That's a different university, and he works at REDS Institute from that's HEIGVD. I don't know this institute, but well, Oscar, would you tell us very briefly what this institute is?
It's an institute in the west part of Switzerland, like a Hochschule or something like that. I don't know if it's the same word in German and in Switzerland. And yeah, this is an embedded system department. So they focused in FPGAs and optimizations and stuff like that, and also in SDR.
Okay, very interesting. Very interesting. So, well, okay, dear audience, you know the procedure anyway. You've been able to follow that also in the past talks. We have also pre-recorded this talk, and we're going to hand over the camera and control over to our video team, and the video team is going to play the pre-recorded video. You can raise questions in the video chat, and Oscar is going to respond to those questions, and afterwards, if time allows, and if there are any more questions that are that were not answered,
Marcus, would you please explain a little bit about an introduction to the talk?
Yes, sure. Excuse me. Yeah, the talk, the topic is on deep learning, inference, and GNU Radio with ONNX, and yeah, GNU Radio out of tree block. That's a GNU Radio out of tree block, and it's to run a deep learning inference inside GNU Radio using the ONNX Runtime. And deep learning is a branch of machine learning that has been used successfully to solve complex problems in different domains like image processing, natural language processing, and speech recognition. And in recent years, deep learning techniques have also been applied to wireless communication and spectrum sensing, spectrum monitoring, and showing that it can outperform classical approaches in tasks like automatic modulation, classification. And integrating such technology in a software-defined radio context is very promising, and it could lead to opening new possibilities in the field, for instance, in cognitive radio and signal classification. That's highly interesting, and I'd like to make a reference to Florian Brauchle, who was also thinking about such things. We have developed, Oscar and his team and Alberto Dassati, they've developed an OOT module that integrates a deep learning inference engine that uses the Open Neural Network Exchange ONNX format and different graph optimizations and accelerators to improve inference performance. And ONNX has support for most of the major deep learning frameworks and provides framework interoperability. And the ONNX Runtime supports different optimization techniques, hardware, accelerators, and backends. And the talk will demonstrate its functionality in the radio flowgraph, running classification using a simple deep learning model, a raw IQ values acquired in this case from a PlutoSDR. That's very fascinating because we're now merging artificial intelligence and the radio domain. Really fantastic. So sorry that I didn't say about introduce the contents, but now your talk is coming, and we're handing over the camera to the video team. Sebastian, please go ahead.
Okay, hi, my name is Oscar. I work at the REST department of HEIGVD, and we are going to show you how you can integrate deep learning and software-defined radio. This is the result of a project named SDR Makerspace by the LibreSpace Foundation. You can search for it and find more information about it. What we did is we have implemented a GNU Radio out of the tree block that encapsulates and integrates a deep learning inference engine. It allows you to easily include deep learning and machine learning solutions for the SDR thanks to GNU Radio and ONNX Runtime. We also have prepared an example where we show you how can you use it in a real example with a deep learning model for automatic modulation classification in GNU Radio and with an SDR device. Communication and signal processing methods are typically based on statistical models that approximate and estimate a real environment. This approach provides optimal algorithms with controllable complexity. These models perform very well, but they make assumptions and estimations about aspects like channel behavior, noise distribution, or distortion that might not accurately represent the real environment, and therefore, the performance of these models deteriorate. Here is where machine learning, and especially in the last years, deep learning, can be a powerful tool because they don't rely in a statistical model and its assumptions, but rather learns it from actual data, addressing this way actual real modeling issues. Furthermore, we can combine model-based signal processing and deep learning to benefit from both worlds because they are not incompatible solutions. Machine learning can help to design and optimize communication networks as it has been shown for channel estimation, detection and decoding, beamforming, insecurity for jamming detection and anti-jamming strategies, device fingerprinting, resource allocation and opportunistic access to the spectrum, traffic classification. There are a lot of examples where machine learning is very useful for wireless communications. And that's why in the last years, more and more initiatives and in the usage of machine learning and radio communications are emerging. Like, for example, the Radio Frequency Machine Learning System program from DARPA in the US. So what is deep learning? We're going to try to give a hint here. Deep learning is a subset of artificial intelligence and machine learning based on the ideas of multi-layer artificial neural networks. In the past decade, deep learning has revolutionized many fields with huge empirical success, especially in problems where modeling is difficult, like in radio communications. We have examples in computer vision and visual recognition, for example, with self-driving cars, in speech processing, in natural language processing, in drug discovery and toxicology, in fraud detection, and a lot more. An artificial neural network are inspired by the biological neural networks. They are composed by interconnected artificial neurons typically organized in layers. The idea is that the neurons on one layer take the values from the previous one and transform them in some way, linear or nonlinear, and then pass them into the next layer. In this example of artificial neural networks, we can find 4 layers. The first layer is the input layer. We have 2 hidden layers concatenated, and then we have one last layer as the output layer. Deep learning models are much more complex, but they follow the same basic idea. The deep part comes from the number of hidden layers because they have many more than 2 layers that we can see in this figure. So in summary, deep learning models, they are a concatenation of multiple parameterized linear or not linear transformations, similar to what we have here in this image of an artificial neural network. To develop a deep learning model, first you have to design your model. The design consists on choosing the architecture, its component, and its hyperparameters. This will define the properties and capabilities of the model. The design phase is driven by the type of problems that you're trying to solve and the data available to do so. Then, once we have designed the model, we can initialize it and start the training process. In the training process, you use known data to modify the parameters, the neural connections between neurons, of the model to optimize, usually minimize a defined loss function. After training you test the model with more known data that was not used during training to get an estimation of the performance of your trained model. You usually repeat those steps, training and test, a couple of times until you get a good performance. And then you optimize in general your model in an iterative process, going back to the design phase and then train and test again. Once you have an optimal trained model, you can use it for inference with new and unknown data. The highly flexible architecture of deep learning models can learn directly from raw data, and their performance increases when you provide huge amount of data for the training. One of the most interesting capabilities of deep learning is that they can automatically learn representations or features during training from the data without hand-coded rules or human domain knowledge. A deep learning framework is a software platform that facilitates the design and development of deep learning solutions. It provides the functionality needed to carry out all the phases in deep learning development that we saw in the previous slide. There are many different frameworks that provide more or less similar capabilities for deep learning development, but the main problem is that they are incompatible among them. This means that you are tied to the framework that you have chosen for the development of your deep learning model, and you cannot move from platform. Our solution in this case to solve this incompatibility is to use ONNX format and ONNX runtime for inference. ONNX, or Open Neural Network Exchange, is an open format built to represent machine learning models. Open format means that it's not tied to a company and anybody can use it freely in their projects. The main advantage here is that it provides a framework in interoperability, meaning that you are not tied anymore to a single framework. And you can use your preferred deep learning framework to design, train, and optimize your model, and then transform it into ONNX. Other advantages are that it is widely supported by most of the most used deep learning frameworks nowadays. It is developed by Microsoft, and it's backed by big players in the market. And yeah, it is even natively supported by frameworks from other companies. And also, it is actively developed, which means that Microsoft is putting the resources behind this project. So there is somebody developing it. Some of its disadvantages are the overhead of transforming your model into ONNX format, compared with having everything inside of the same platform, so you don't have to move. And also the operation availability. This means that not all the operations from all compatible frameworks are available on ONNX, but we will speak about this later. Here we can see a list of the compatible frameworks of deep learning frameworks provided by ONNX. They are either natively supported, like for example is the case of PTorch by Facebook, or some kind of converter is provided by ONNX. So for example, we have the most used deep learning platforms nowadays, which are TensorFlow and PTorch and maybe Keras. And even we can develop our model, and we can develop and we can design, train, and test our model in MATLAB, and then move it to ONNX. So we have flexibility to choose our desired deep learning framework. All deep learning models are built with the same basic building blocks, but different platforms define their own blocks. In this example, we have a part of a TensorFlow model on the left, and its translation in ONNX on the right. We can see, for example, that here in TensorFlow, the activation function is included inside the convolutional block, and in ONNX, the activation function is independent. is an independent operation. Here, for example, in TensorFlow, we can see that a dense layer in TensorFlow is equivalent to a matrix multiplication, an addition, and an activation function in ONNX. This means that all the functionality in the supported frameworks have to be available in ONNX, either with an independent operation or decomposed into basic operations already supported in ONNX. But that is not always the case, and you can find that the model design with one framework cannot be translated into ONNX. This is due that ONNX might be a little bit behind the latest versions of the supported deep learning frameworks, but usually they catch up really, really fast. So now we have ONNX Runtime. ONNX Runtime is a high-performance and cross-platform inference engine developed by Microsoft for ONNX models. It has interfaces in Python, in C and C++, and in the last versions, they also added interfaces in C# and Java. It supports multiple hardware accelerations, and it provides an extensible architecture. We will see this in the next couple of slides. Here we can see more or less a high-level diagram of the architecture of the ONNX Runtime. You can see that once an ONNX model is read by the ONNX Runtime, it's divided into different parts and then scheduled to run in parallel, if possible, by all the available execution providers. An execution provider is an abstraction and runtime support for custom accelerator and runtimes. And ONNX Runtime is able to execute a single ONNX model in an heterogeneous environment involving multiple execution providers. This means that all the different operators that we've seen in the previous slide can be executed in parallel and in different execution providers at the same time, providing a high performance. Here we have the list of the ONNX Runtime accelerators supported by default in ONNX Runtime. We have some of them are optimized libraries for specific mathematical operations. Some of them are specialized in the usage of some specialized hardware, like the GPUs, the graphical processing units, the NPUs, which is neural processing unit, or even FPGAs, like is the case of Xilinx BTs. And some of them also perform optimizations at inference time, like is the case of NVIDIA Tensor RT. But yeah. Acceleration, it's a really important aspect of deep learning because due to the complexity of these deep learning models and the huge amount of data required to get good results, the performance needed it gets out of hand if you want to something close to real time. So basically, what we did we developed a GNUradio out of the tracing module that encapsulates an ONNX runtime, allowing an easy integration inside a GNUradio of deep learning inference. It's developed in Python using the Python interface of ONNX runtime and the Python interface of GNUradio. The Python interface of ONNX Runtime requires Python 3.something, which means that our module requires a GNUradio version 3.8 or greater. The input of our module is an n-dimensional interleaf float vector. This means that if you have more than one dimension in your input, you will have to interleave it until you have a prime vector. So for example, if you are using, I don't know, 1000 FTT features as input, you won't have to do anything because that's a plain flattened vector, so you won't have to do anything. But for example, if you are using raw IQ samples, we will have time and we will have IQ, which means that we will have to interleave IQ samples every time step in order to pass it to our block. And then we will have a single dimensional float vector as an output of the module. We also support the hardware accelerator supported by ONNX Runtime. In order to configure our module, what you need is the ONNX model, and of course the path to your model. The batch size. The batch size is the number of elements that will be used to run inference at once. This helps to reduce the overhead of moving data between different devices like a CPU, the GPU, and FPGA, and optimize the hardware acceleration. Then you will need the input side of one flatted element of the input of the model. So for example, as I said before, if you are using 1000 FTT features, then the input size is 1000. But for example, if you are using 1000 IQ values, the size is 2000 because you are using 1000 I values and 1000 Q values. Then you have to configure the output side, which is the actual output side of the model, and it will depend on the problem that you're trying to solve and the design of your model. And then you will have to choose the device preferred to run the inference. So you can take advantage of the hardware acceleration that we mentioned before. Now we're going to present you the example that we prepared to show the capabilities of the block that we have developed. We took an article from Timoshi with the name An Introduction to Deep Learning for the Physical Layer. This article proposes to use a convolutional neural network for modulation classification of single carrier modulation based on sampled radio frequency time series data, which are raw IQ samples. They provide the simulated data. They provide the simulated data of the chosen modulations simulated in GNUradio, and they also suggest they also provide with a deep learning design. And what we did is we tried to reproduce what they propose in their paper using the data that they provide. So we took the design that they propose, we coded in TensorFlow, then we used the provided data, which are raw IQ samples, raw IQ samples of 1024 length, and then we will try to classify into 11 different single carrier modulations. Then once we have trained the model in TensorFlow, we transform it into ONNX with a converter tool provided by ONNX team. And then finally, we are ready to use it inside GNUradio. This is the flow graph of the automatic modulation classification on GNUradio. Here we can see the SDR source. In this case, is an Adam Pluto board. The output of this block is it's a stream of IQ complex values, which we pass to a waterfall for visualization, and also to the data preparation of our flow graph. In order to prepare the data for our block, what we do is we take the stream of complex IQ values and we transform it to float values. So we have I and Q. Then we interleave it as we said, and then we transform the stream of interleave IQ values into vector of the correct size that we will pass to our model. Here we can see that if we are using 1024 IQ samples, the input size of our block will be 2048. the output will be 11 float values, because that's the number of modulations that we used in training. We're going to use a batch size of 300 samples, and we're going to use the GPU for inference. Then we take the output of our model, which are the probability of belonging to one of those 11 different modulations, and we transform it into a stream in order to pass it to a raster sink for visualization. One important aspect here in the raster sink is that we choose the number of columns the same as the output length of our model. So the offset in the visualization, it's each column corresponds to one class, but we can see it here better. This is the output of our GNUradio flowgraph for automatic modulation classification. In the top, we can see the output of the SDR device, the raw output of the SDR device. And in the bottom, we can see the output of our model. We did some drawing here to facilitate the reading. Here we have the different classes that we use during training of our deep learning model. So we have 11 different classes, which corresponds to 11 different modulations. In the y-axis, we have the time, and the color here is the probability of belonging to one of these classes. So here you can see how different samples are classified in different modulations. This is just a toy example on how can you use this kind of module easily inside of GNUradio for deep learning inference. And you can find all the code following this URL. Not only the code, you will find the documentation for how to install it, and a lot of explanations. Examples, not only the example that we show, we also have more examples. You can also have toy models that you can just plug in the module, and you can find also Docker images to run these experiments out of the box. I don't know if you're familiar with Docker, but it's quite easy. And the future of deep learning and machine learning in radio communications, we think that it's quite promising. We are seeing more and more publications using deep learning and machine learning in this context. So we think that our blog can be very useful for these people. And we have to consider that ONNX and ONNX Runtime, they have a high pace of updating. So every couple of months they release a new update, and of course, if we want to support the new functionalities, we have to adapt our blog. And also something that we can work in the future is to provide more flexibility for more complex deep learning models, because the reality of deep learning is that there are very, very, very complex models that we don't support with the current module that we have, but that's something that we have to consider, because then the configuration of the blog will be much more complex than what we have. So that's it. Thank you for your time. And if you have any questions, those are more than welcome. Thank you very much.
Thank you very much for this really thrilling talk, Oscar. I'm by education, I'm also a computational linguist, and we've been doing quite a lot with artificial intelligence and a lot of statistics also at our institute at Munich University. So I do understand absolutely what you've been doing there in your research. That's really fantastic, absolutely fantastic. And I had the feeling that artificial intelligence should have an interconnection with software-defined radio and numeric analytics and so on. That's really, really interesting. This is the first time I see it happening, really. Somebody's doing something about this, and it's really very, very good. So great applause from me here.
Thank you.
Absolutely. Absolutely great. So you've been responding to all the questions in the video chat, I see. We're running a lot of time in this slot. It's 15:30 here. So we'll have to change over to the other studio where our next speaker is already waiting. So we don't have any more time here to discuss these really fantastic developments, but I would like to thank you very, very much for coming in and giving this talk and responding to our community here. This is really a so thank you very, very much, and I hope we'll stay in contact, and I hope we'll see you again here next year. And okay, my studio team is already changing rooms.
Thank you for your work and all the work that you done with the talk. It was very, very nice to work with you.
Thank you also. So thank you very much and see you again. Have a nice day.
Thank you.
A big applause. Thank you. Bye-bye.
Okay, goodbye.
Bye.